Hello everyone, welcome to the Monthly Virtual. Hope you are doing good. Today I am going to start with chapter number 3, that is machine level representation of programs. So, in yesterday's class I have finished with chapter number 2. So till now I have finished with two chapters, that is chapter number 1 and chapter number 2. So let's take quick review or quick recap of the previous class, that is yesterday's class, what we have covered in the yesterday's class. So let's take a quick review of the previous class. In previous class we discussed what is the floating point number, how we can use the floating point number. So floating point number is nothing but a number that is in fraction. So whenever I use decimal number system, that is known as floating point number. So this is, it describes a method of representing an approximation of a real number in a way that it can support a wide range of values. The numbers are in general represented approximately to a fixed number of significant digits. And this is the equation of the floating point number. Then we have talked about what is the standard that is available for floating point number that is used in computer system. This is the standard named IEEE 754. The full form of IEEE is Institute of Electronic and Electrical Engineers. Either I can use electrical and engineer. Either I can use electronic and electrical or electric and electronical engineer. This is a standard that is used by almost every computer except IBM, because IBM uses its own computer where there is the T90 series of the IEEE version. There are multiple types of formats available which we have covered yesterday. There are two types of format. One is basic, one is extended format. Basic format includes 5 types of format, and that includes single precision and double precision, double extended precision. So there are multiple types of precision. One is double, one is single, and one is double extended. This is double extended precision. Then we have talked about what is a fractional number system, means how we can use fractional number system in computer system, or fractional binary number. Till now we have discussed what is how we can use integer arithmetic. Now this chapter is how we can use fractional binary number. This is in mathematical and digital electronics, a binary number is a number expressed in binary number system or base 2 number system which represents numerical value either using 0 and 1. So binary number system is a number that has a value either 0 or either 1. Then we have talked about how we can use the fractional binary conversion. This is the method how we can use the fractional binary conversion. This is the method for decimal binary conversion. This is the method. And this is the method for binary conversion. So this is the used for decimal, that is 1 by 10, 1 by 100, 1 by 1000, and this is used for binary, that is 1 by 4, 1 by 8, 1 by 2, 1 by 4, 1 by 8, 1 by 16, and so on. This is used in fractional binary representation. This is the method how we can use. Next is your binary fractions. There is a binary fraction as I told you, 1 by 2, 1 by 4, 1 by 8, and 1 by 16. So this slide shows how we can use the binary conversion, how we can convert the decimal number system into the binary number system or binary number system into the decimal number system. But the main limitation is that it provides less accuracy because there is a decimal number system, there is a round of figure, and whenever we use decimal number system, the problems, the questions, the digits automatically rounds off. So that creates a problem, or that creates a less accuracy as compared to the binary number system that is in integer form. This is an example how we can convert decimal number system into the binary number system. This says we are going to convert 6.125 into a binary fraction. So this is an example for 6.125. This is 4, this is 2, this is 0.125. And we also discussed what is IEEE floating point number. This is an example how we can use the floating point number. This is defined by IEEE standard 754. These are the examples of floating points. Then we also talked about how we can round off the function. So the main thing or main crux is that whenever I have to find the round off figure, suppose this is the second figure after decimal. So look over to the another digit, means the right side of the digit for which I have to round off. So another digit is 7, so the round off is 4 is converted into 5 because the next digit or the right digit is greater than 5 or equals to 5 but it's greater than equals 7, so the figure is my 23.45. But if it is less than 5 then the figure is same 23.5, 23.44. So the main target or main crux is that whenever there is a figure, whenever there is a digit that is greater than or equal to 5, then automatically the previous digit or the left hand side digit will automatically increase. But if the digit is less than 5, then the value is remain same and it does not increase automatically. There are multiple types of rounding problem that is available. Whenever we divide an irrational number by a fraction, this is also an error. Replacing a rational number by a fraction, this is also an error. There are multiple types of rounding problems that we face while using the rounding method. Then we also talked about what are the operations available or what are the operations that we perform on the floating point numbers. As there are so many operations like addition, subtraction, multiplication that we performed on integer values, in the same way we can perform multiple operations like integer, subtraction, multiplication, division with the help of floating point number that is in decimal form. This is the example for addition. There are multiple steps. First step says align decimal points. This is the alignment of the decimal point and then add. This is the step how we can align. First of all, convert either first equation into second equation or second equation into first equation. Like 3.25 into 10 power 3. Second one is also converted into, this is divided by 1000 because this is 10 power 3. So 0.0006263 into 10 power 3. Now add these values to these values. Second step is your addition. This is the addition, this is the addition. Next is the multiplication. The process same algorithm, that is multiply the Mantissa part. This is the Mantissa part. First of all multiply the Mantissa part. Then second point is that add the exponent part. Means we have to multiply the Mantissa part but we have to add the exponent part. This is the multiplication Mantissa. So multiplication is 3.0 into 0.5 is 1.50. And the exponent part is added, that is 2 plus 1 is 3. This is 1.50 into 10 power 3. This is in binary example. This is in binary example. Then we have also talked about how we can represent the floating point in C language. This is the example how we can represent. This is another example. So this is what we have covered in the last class, that is in the previous class. Today I am going to start with chapter number 3 and this is one of the important chapter that is available, that is machine level representation of programs. As the name advises, machine level representation means how we can represent the program. First of all, what is a program? Program is nothing but a series of instructions which are given to the user or which the user gives to the another user. So whenever we represent the program in machine level language, that is known as machine level representation of programs. Machine level language means in either 0 or in either 1 form. So it is also provision we can represent the programs in machine level language, in assembly level language, in any kind of programming language. This chapter gives an overview of the assembly language, C language, as well as the high level languages that we use in the computer system. And this also shows how we can format the data, how we can link the data from one form to another form. So starting with first topic, that is your assembly language. But before this, let's take this review. This one is assembly language. These are the multiple programming languages. First of all, there is a hardware which we can use. There is a machine language that computer uses while representing in either zeros and ones. That is your machine language. Next is your assembly language that uses mnemonics, which I will tell you within 5 minutes. Mnemonics for writing the program, for writing the codes of the program. Then next is your high level language that is used for writing the programs like C, C++, in which there is a predefined syntax. Predefined syntax means syntax is already available. We have to use the syntax. We have to use the same format, but my digits or my argument are different. I'm repeating again. High level languages contains predefined syntax. Predefined syntax means there is predefined format available. We have to choose the format but change the argument or the digits that is available in programming languages. So there are so many kinds of multiple types of programming languages, and one of the example which I am going to tell in this chapter is assembly language program. This is the high level languages like Fortran, C, Pascal. There are so many languages that is available. I am repeating again, that is Fortran, C and Pascal. So these are the multiple programming languages that is available in computer system. Now let's start with assembly language, because this chapter focuses on the assembly language. So assembly language is nothing. It is a programming language. Programming language means that the programmer uses for writing the programs. They said this is a programming, low-level programming language for a computer or other programmable device in which there is very strong, generally one-to-one correspondence between the language and the architecture machine code instructions. So assembly language is a low-level programming language that the programmer uses for writing the programs or any other programmable device in which there is a strong means there is one-to-one correspondence between the language and the architecture. So this means that there is one-to-one correspondence means whenever we have to put the data in hardware, in some hardware, so that can be denoted by assembly languages. So the assembly language provides direct communication, direct correspondence between language and the architecture of the computer. Next line says, each assembly language is specific to a particular computer architecture. In contrast to most high-level programming languages, which are generally portable across multiple architectures. So this says every assembly language is specified or particular or applicable only to a particular computer architecture, as comparison to the high-level languages that is suitable for each and every architecture. But that high-level languages require compilers and interpreters. As I told you while I am giving the overview of programming, there are two system tools that is available for converting them to machine-level languages, that is interpreter and compiler. Compiler interprets or compiler converts the code into binary terms, the whole program at the same time. This means compiler compiles the program or translates the whole program at the same time at the one go. Means in a one go it converts the whole program into bits, that is 0 and 1, so that computer can understand bits and perform the operations. On the other hand, interpreter is the system tool that is similar to the compiler that converts high-level languages into machine-level languages, that is 0 and 1. But the main difference is that interpreter perform all the tasks line by line, means it converts the whole program line by line into machine-level language, but compiler converts whole program, means the full program at one go. So the main difference is clear, I think. Compiler or program at the same time, interpreter one program at the same time, or sorry, one line of the program at the same time. So if I have to use high-level languages that is used in every architecture, but the main limitation or the main target or the main foundation is that we can use, or we are supposed to use compiler and interpreter for converting into machine level language. Next is assembly language is converted into executable machine code by a utility program refers to an assembler. Like which I told you, there is a compiler and interpreter that converts high level languages into machine level languages. In the same way, there is another tool, there is another term that is known as assembler that converts the program into the machine code, or the assembly language program into the machine code. The conversion process is referred to as assembly or assembling the code. So this paragraph, this slide only talks about what is assembly language, how we can use assembly language. Assembly language is applicable on multiple architecture or not. And there are three system tools available. One is compiler, one is interpreter, and one is assembler. Compiler converts the whole program of the high level language into machine level language. Interpreter converts the whole program or the program line by line at one time. Means it compile or it translate into machine level language line by line. First of all, one line will translate it, then another line, then next line, then next line, and next line. So that is known as interpreter. So compiler, interpreter. Next, the next term is your assembler that converts assembly language program into the machine level language program. Assembly language program means which is written in assembly language, that is known as assembly language program. But for compilation, for execution, it must be converted into executable code or machine code, and that is provided by assembler. Next is assembly language uses mnemonics. Here M is silent, we can say or we pronounce as mnemonics to represent low level machine instruction or operation. So in C languages, as I told you, there are multiple syntax like printf, scanf, for, if. So that uses multiple commands or multiple operations. But if I want to write the code or the program into assembly language, so assembly language uses a mnemonics to represent each low level instruction or operation. Typical operations require one or more operand in order to complete or form a complete instruction. And most assembler can therefore take labels, symbols, and expressions as operand to represent addresses and other constants, freeing the programmer from tedious manual calculation. This paragraph says there is a tool or there is a code that is known as mnemonics. The assembly language uses mnemonics for writing the program that is used for taking the labels, symbol, expressions to represent the addresses and other constants that allows the programmer to write the code very easily instead of the manual calculation. Suppose I have to calculate the values, or I have to calculate the sum of two numbers, or addition of two numbers, multiplication of two numbers. So I can do it in manually, but this is also represented by using the program that is in either C, C++, that is high level language program, or in either using assembly language program that uses mnemonics for writing the program. Next line says macro assembler includes a macro instruction facility so that assembly language text can be represented by a name, and that name can be used to insert the expanded text into another code. Many assemblers offer additional mechanisms to facilitate program development to control the assembly process and to aid debugging. Means many assemblers that is used in assembly language are required to facilitate program development, means how we can develop the program, to control the assembly process and to aid the debugging process. This is the diagram which I shown you. Now next is how or review of assembly language. The first point is that program text contains binary instructions. This means CPU executes one instruction at the same time, usually executes next sequential instruction in memory. Next branch, jump, call ins specifies different next instruction. So these are the mnemonics like branch, jump, call list or call ins that is used in writing the assembly language program or assembly language code. Next set, assembly language instructions typically manipulate, or we can manipulate the instructions of the assembly language very easily. There are so many instructions that is available. One is known as registers that contains small number of values kept by the processor. Next is your memory that is used for storing the data, for storing the program into the computer memory. Then there is a special registers whose bits have particular significance, which I told you in the last class. There are two types of bits. One is unsigned integer, one is signed integer. So this assembly language uses special registers that contains only these two types of languages, these two types of bits, that is unsigned bits and signed bits, or unsigned integer and signed integer. Next is the IP, that is instruction pointer, which instructs to execute next is your input output devices. So these are the instructions that is available in assembly language program for writing the programs. So this is a review of assembly language. Next is there are two types of mode, means how we can store the data in assembly language. One is your real mode, one is your protected mode. Now let's see what are the two types of modes that is available in assembly language program. First one says is real mode. This contains 16-bit registers, 1 MB virtual memory. So this contains this uses real mode contains or uses 16-bit registers. As I told you, there is a memory hierarchy, that is registers, cache memory, RAM, secondary memory. So real mode uses only 16-bit registers and 1 MB virtual memory. I also already told you what is virtual memory. Whenever there is a extra space required beyond the main memory, then use the virtual memory for storing the data and instructions. Next, real mode. This contains 16-bit, 1 MB virtual memory. Next is segment registers provide top 4 bits of physical address. 4 bits means total how many bits? 4 bits. That is either 0, 1, 0, 1, 0, 0, 0, 0, 1, 1, 1, 1, or either 1, 0, 1, 0. It may include any type of comparison, any type of similarity that uses, or any type of grouping. Then next point is, this is probably what you have used in earlier classes. This is nothing but probably what you have used in earlier classes. Now let's take example. This is move W percentage AX, means we can move the data, that is move percentage AX, move W AX, comma percentage DX, means DX equals to star int 32T star 16 into DS plus AX. So this is how we can represent the real mode in assembly language program that uses 16-bit register and 1 MB virtual memory. Then next mode is your protected mode. That is segment register virtualized, means all the registers, all the segments are stored in register for storing the instructions. That loads segment register from table of segment descriptors. Depending on percentage descriptors, default ops can be 32 bits. Next is 32-bit virtual address space can optionally be paged. This requires 36-bit physical address space depending on the mode. Mode means it may be in read mode that only reads the data, it may be in write mode that only writes the data, or it may be in execute mode that only executes the data. Then next point says we will mostly use 32-bit protected mode. There is also a optional or options, but we are generally mostly use 32-bit protected. All remaining example will be 32-bit code. More 32-bit instructions. This is ALU. ALU means arithmetic and logical operations. We can perform the operation. This is OPS means operations, that is add 1, sub 1, handle. So this is add 1, sub 1, and 1, or 1 means or operation, which I told you there are multiple operations like AND, or, XOR, and NOT. Increment, decrement, add or subtract. This is comparison like sub but discard subtraction result. And another 32-bit instructions are stack instructions and other stack instructions like push, push AL, push FL. This is push HL or push L, pop L. So these are the 32-bit instructions, and we generally use 32-bit instructions in assembly language program that is used in writing the assembly language codes. So these are the multiple 32-bit instructions. Now let's see in your book. This is your starting of the chapter. There are total 14 or 15 topics. Yeah, 15 topics. One is your historical perspective, which I told you what is the family language, what is the history, how many bits are available. Then program encoding, how we can write the assembly language program code, data format, assessing information, arithmetic and logical operations, control, procedures, array collection or allocation, heterogeneous data structure, putting it together, life in the real world using the GDB or debugger, out of bounds, x86, machine level instruction. Then there is a summary part. So these are the topics that we can study in this one. Now let's start with this paragraph. This is one of the important paragraph. This says computer executes machine code that contains sequence of bytes including the top level operations that manipulates data, manage memory, read and write data on storage devices, and communicate over the network. A compiler generates machine code through a series of stages based on the rule of programming languages, programming conventions, and that is followed by the operating system. This says till now we are using machine level code that programmer uses for writing the program. The GCC C compiler generates its output in the form of assembly code, a textual representation of the machine code giving the individual instructions in the program. So this compiler generates its output in assembly code. GCC then invokes both an assembler and the linker to generate the executable machine code. As I told you, assembler is used for converting the assembly language into the machine level programs. In this chapter, we will take a close look on the machine code and its human readable representation as assembly code. So this is a paragraph, this is a theory, how we can use the C language, what is the high level language such as C, Java, Fortran. Next paragraph says, in this chapter we will learn the details of two particular assembly languages, that is IA32 and x86, and see how C programs get compiled into these form of machine code. So in this chapter we will study only two types of assembly language program, and on the basis of these assembly languages, how we can compile the C program in the form of machine codes. So this says reading the assembly code generated by a compiler involves a different set of skills than writing assembly code by hand. So whenever we write assembly code program by compiler, that requires much opportunities, much behavior than when we write the assembly code by hand. These are the same theories. Yeah. This says our presentation is based on two related machine languages. As I told you, there are two types of machine languages or assembly languages. One is IA32, that is the dominant language of most computers today, and x86-64, that is extension to run on 64 bits. IA32 only runs on 32-bit operating system, but x86-64 runs on 64-bit operating system, means it is an extension to run on the 64-bit machines. Our focus starts with IA32. Intel processors have grown from the primitive 16-bit processor in 1978. So this paragraph explains you how we can move from IA32 to x86-64 whenever there is a requirement or whenever there is a starting phase of the computer. At that time, computer requirement, computer memory are not good. So we can use, or we are using, only 32-bit registers or 32-bit operating system. But now, as the time grows up, there is also a new provision, so we can use 64-bit registers. So there are only two types of, or two kinds of machine languages or assembly languages that we can use, that is IA32 and x86-64. Our focus starts with IA32. Intel processors have grown from the laptop and server computer. The architecture and grown correspondingly with new features added, and with the 16-bit architecture transferred to become a IA32. As I told you before this time, there are so many computers which uses 16-bit, 32-bit, 64-bit. So that starts with, or that added with, or starts with 16-bit register, and then new features are added with 16-bit register, that becomes IA32. That supports 32-bit data and enters. We will focus on the subset of the features used by this. Next paragraph says, as we discussed, the extension of IA32 or 64 bits means whenever we extend the IA32 to the 64 bits, that is termed as, that is known as x86-64, was originally developed by AMD. Means the x86-64 is developed by AMD, that is Advanced Micro Devices. Intel bigger competitor, whereas a 32-bit machine can only make use of around 4 gigabyte. 4 gigabyte means that is 2 power 32 bytes of random access memory. Current 64-bit machine can use up to 256 terabyte, that is 2 power 48 bytes. So we can use, or we can may use 32-bit register, 32-bit machines that takes only 4 gigabyte, that is 2 by 32, and 64-bit machine requires or uses 256 terabyte, that is 2 by 48 bytes. This says most of the microprocessors in recent server and desktop machine as well in many laptops supports either 32-bit or 62-bit, 64-bit operations. So the main crux is that there are two types of assembly language, that is IA32 and x86-64. IA32 uses only 32-bit address for instructions and data, and 64-bit uses 64 bits for instructions and data. And that is developed by AMD, that is Advanced Micro Devices. Next is your historical perspective, which I told you what is assembly language, what is x86, how we can start it with. So this says I started with one of the first single chip, that is 16-bit microprocessor. As I told you, it started with 16-bit, then goes to 32-bit, then goes to 64-bit assembly language programs. Now, these are the multiple codes, these are the multiple representation, how we can represent in assembly language. These are the multiple historical perspectives. So it started with first one, that is, this says the list that follows shows some model of Intel processor. I mean, this is the history how we can go from 16 to 32 bits and 32 to 64 bits. This says this model contains some models of Intel processor and some of their key features, especially those affecting machine level programming. We will use the number of transistors required to implement the processor as an indication of how they have involved in complexity. K denotes 1000 and M denotes 100,000 or 100,000. So starting with first one, that is first instruction or first model of Intel is 8086. In bracket, it is mentioned it is available in or it is developed in 1978 and it contains or it have only 29K transistors, means 29,000. K means 1000, so it is contains only 29,000 transistors. This is one of the first single chip. As I told you, this is the first chip that is of 16-bit microprocessors. 8088 is a variant of 8086 with the 8-bit external bus. So first one is 8086, then 8088, that is an extension for 8086, formed with the heart of original IBM personal computer. So this is the main organization, big company that produces multiple codes for assembly language program. IBM contracted with the then tiny Microsoft to develop the MS-DOS operating system. These are the history. Means first of all, 8086 arrives, that is in 1978. That is done by or developed by IBM personal computer. Then IBM personal computer is merged with Microsoft to develop the MS-DOS, that is Microsoft Disk Operating System. The original model came with 32,768 bytes of memory. But now, this is a new concept. We move from one place to another. We move from one location to another. So this introduced new concept for assembly language program. Next, Intel also produced 8087 floating point compressor that requires 45K transistor. Next is your 80286 that is available or developed in 1982. So this is developed in 1978, this is developed in 1982, that requires or that contains only 134K transistors. This is 29 transistors, 29K, this is 45K. Hello, hello. Next is your 80286 that is developed in 1982 that contains 134K transistors. That added more and now obsolete addressing modes that is form the basis of IBM PC-80 personal computer. That is the original platform for MS Windows. So Windows operating system is developed by using 80286. Next one is your i386. that is developed in 1985 and that requires 275K transistors. So these are the multiple history that is available, that how different transistors or how we can generate multiple coding or multiple programming languages. So next one is your I386 that is developed in 1985 and that requires or that have only 275K transistors. This expanded the architecture to 32 bits. Till now the architecture is of 16 bits, but now in I386 the architecture is converted or expanded to the 32 bits. Next is your I486 that is launched or that is developed in 1989 that requires 1.2 M. Now 1 M is 100 or 10,100,000. So I486 is developed in 1989 and have 1.2 M transistors. This says this improved performance and integrity the floating point unit onto the processor chip but does not significantly change the instruction set. So this means with the help of I486 the floating point numbers can easily be represented and that requires only 1.2 M transistors. Next is your Pentium. As you know, there is a Pentium processor. So that Pentium is launched or available or developed in 1993 that requires 3.1 M transistors. This also improved the performance but only added minor extension to the instruction set. Next one is your Pentium Pro that is launched or that is developed in 1995 that requires 5.5 M transistors. This is a new processor design internally known as P6 microarchitecture that added a class that is known as conditional move instruction to the instruction set. So these are the multiple histories starting with 8086, then 80286, I386, I486, Pentium, Pentium Pro. Next is your Pentium 2 that is developed or launched in 1997 and that contains only 7 M transistors, means 7,100,000 transistors, that is in continuation of Pentium 6 micro architecture. Next one is your Pentium 3. Pentium 3 that is developed in 1999 and that requires or that have 8.2 M transistors. 8.2 M is 80,100,000 or 80,120,000 M transistors. This is introduced or this introduced SSE, that is a class of instructions for manipulating vector of integers or floating point area. So with the help of Pentium 3 we can manipulate vectors value of integer value or floating point value. Means we can represent the vector of floating in machine level language, assembly language with the help of Pentium 3 processor. Next is your Pentium 4 that is developed in 2000 that requires 42 M transistor. This is extended to the extension of the SSE and that converts into SSE2. That adds new data types such as double precision or floating point, which I told you in the last class. Double precision, double extended precision, single precision, floating point precision, along with the 144 instruction for these formats. With these extensions, compiler can use SSC instructions rather than x87 instructions. Means rather than using SSC instruction, now compiler or interpreter or system tools uses x87 instruction for compilation the floating point code or for compiling the floating point instructions. Next is your Pentium 4 that is launched in or that is developed in 2000, that is year 2000, and that require 42M transistors. This is an extension for SSE2, SSE2 that is used for compiling floating point codes. Next is your Pentium 4e that is or this is an extension of Pentium 4 that is Pentium 4e. This is developed in 2004 and contains 125M transistors. That is, it adds hyper-threading. As I told you, thread means we can run the same process or we can run the multiple parts of a process at same go. Means executing the different units of the program, different units of the functions at same go. So this is a method to run, which I told you, two programs simultaneously on a single process. So Pentium 4e launched multitasking or multi-programming, that is 2004 125 ME or M transistors. Intel implementation of a 64-bit extension to one IA32 developed by AMD, that is Advanced Micro Devices, which we can refer x86-64. So here 64-bit register, that is Pentium 4 is Pentium 4e in this x86-64 is launched. This is the main history. Then next one is the Core 2 that is launched in 2006 that contains 291M transistors, that is similar to P6. Next is your Core i7 that is launched in 2008 that require 781M transistors that incorporate or that includes both hyper-threading, means more than one programs are running at the same time or simultaneously, and multi-core with the initial version supporting 2 executing programs on each core and up to 4 cores on each chip. Means in this we can execute more than one program as well, and we can execute large number of programs at the same time, as well as we can use multiple chips in the processor, in the RAM, in the hard disk at the same time. So this is the main history, how we can implement or how we can use or how we can go from IA32 to x86-64. These are the multiple details. So this says each successive processor has been designed to be backward compatible, able to run code compiled for any earlier versions. This is Intel architecture 32-bit, that is IA32. That is extended to 64, that is known as x86-64. So this is the figure. This is the figure of the history. First one is 8086, then 80286, i386, i486, Pentium, Pentium 2, Pentium 4 Pro, Pentium 3, Pentium 4, Pentium 4e, Core 2 Duo, Core i7. These are the multiple figures that is available by year or year wise. Now next is your program encoding, means how we can write the program in assembly language program. But before this, let's take a 10 or 5 to 10 minutes break, and then after come back starting with second topic, that is programming encoding. So let's take 5 to 10 minutes break. Now let's start with second topic, that is program encoding. So this topic is related to whenever we write the programming assembly language program or whenever we write the coding assembly language program. First one is your machine level code that requires IA32, IA32 editor. Now let's see with the help of slides. Now there are again some few concepts that is available. One is known as assembler. As I told you, assembler is a program that converts assembly language program into machine level language program. This is a program, assembler is a program which creates object code by translating combination of mnemonics and syntax and for operations and addressing modes into their numerical equivalent. So this is a program, assembler is a program which converts mnemonics and syntax or which converts mnemonic into multiple operations into machine level language programs. This representation typically includes an operation part known as output as well as other control bits. The assembler also calculates constant expressions and resolve symbolic names for memory location and other entities. So assembler is nothing but a system tool or a program that converts assembly language program into machine level language programs. For example, to generate common short sequences of instructions as inline instead of knowing a subroutine. This is the example how we can use the mnemonics. Next is your number of passes. Means what are the number of passes that is available while executing or while translating or while performing the operations of machine level language in assembly level language programs. There are two types of assembler based on how many passes through the sources are needed to produce the executable program. Executable program means that is in either zeros or ones. So there are only two types of assembler. Two types of assemblers that is required for producing the executable program. One is known as, or first pass is known as one pass assembler that go through the source code once. Any symbol used before it is defined will require errata at the end of object code or at least no earlier than the point where symbol is defined. So one pass assembler is, it goes through the source only once. Means it compiles or it goes through the whole source of the assembly language only once in a lifetime of the program. Any symbol that is defined will require errata at the end of the object code and linker or loader to go back and overwrite a placeholder which is left where the as yet undefined symbol are used. So one time assembler or one pass assembler is simply that focus or that executes or that captures only the program code at least once. And multi-pass assembler creates a table with all the symbols and their values in first passes. So all the values and symbols are separated in the source code, in the object code by using the one pass assembler. Then multi-pass assembler creates a table with all the symbols and their values in that is available or that is fetched from the first pass assembler. Then uses the table in later passes to generate the code. So there are two types of passes. One is one-time pass, one pass assembler, one is multi-pass assembler. One pass assembler uses or compiles the source code only once that separates symbols and multiple values at the end and at the starting of the assembler. And multi-pass assembler creates a table with all the symbols and all the values in the form of a table, and that values and symbols must be fetched from the first pass assembler and then uses that table to perform or to generate the code in the future. Now there are, as I told you, there are two types of assembly language. One is IA32 assembly programming. So let's talk about what is IA32 assembly programming. This chapter is intended to be a reference you can use when programming in IA32 assembly. It covers the most important aspect. This is assembly language instructions. All assembly language instructions, assembler directives means mnemonics and macros uses the following format. So this is the format which is used in IA32. That is Intel Architecture 32 assembly programming. First one is your label, then mnemonic, then operands, then comments. This is the format. This is the most important format. Please see very carefully. One is label, then mnemonic, then operands, and then comments. This says fields in square bracket are optional. Means operands are optional, comments are optional, labels are optional. But mnemonics are mandatory, that is not optional. Then label is used to represent either an identifier or an constant. Then mnemonic, so label is used to either represent either identifier or an constant, and mnemonics identifies the purpose of the statement. I mean, what is the purpose? Why I am using the assembly language code? A mnemonics is not required if a line contains only a label or comment. So if there is a line or there is a label that contains only label or comment, means there is no operand. So mnemonics is not required. So the mnemonics requirement is only with the operands or operators. So whenever they are operand means suppose 2, 3, 4, on which operation has to be performed, that is known as operand. If there is an operand, then mnemonics is used, otherwise mnemonics is not used. Next, operand, as I told you, it specifies the data to be manipulated, like A, B, C, D, 2, 3, 4, 5, that is known as operands. Then comments, that text ignored by the assembler. Suppose I am writing the machine level language code and I am giving or I am mailing the code to you, to any other user. So how any other user or the third person will capture all the aspects, all the terms by simply using the comments or by simply seeing the comments. So whenever there is a comment, that denotes what is flow or what is the flow of the program, what is covered in the program, what we have covered in the program. This gives a detailed explanation or detailed manual about the program. So comments is usually or mostly ignored by the assembler while executing the code. So this is the assembly language statement that is available in IA32. The syntax is label, mnemonic, operands, comments. This is the example. This is a comment. This is a comment example denoted by semicolon. Then jump label 1. This is the label 1, that is jump. This is also a comment. Then add EAX, EBX. This is add is known as mnemonic. EAX, EBX are known as operands. This says labels are in italic. This is in italic. Mnemonics in bold, this is in bold, add, jump, sub, operands are underlined, these are not underlined but this is mentioned underlined, and commands are in regular text. So, I will tell you, JMP is a mnemonic, label 1 is a label, add is a mnemonic, EAX, EBX are operands, then label 1, then subtract EDX32, SUB is a mnemonic and these are known as operands. So, this adds two values or two variables, that is EAX and EBX. So this will add the values of variables, that is EAX and EBX, and the last line SUB EDX32 subtracts the EDX value from the 32. Suppose EDX value have a value 64. So 64 minus 32 is your 32. So the output is 32. So this will use while writing the assembly language program. Next, IA32 is different from the original C. There are multiple other things that is available while I am using the IA32. So first one is your program counter, also known as PC, and known percentage EIP in IA32 indicates the address in memory of the next instruction to be executed. Suppose there are 5 types of instructions that the assembly language executes and I am on second instruction, let's say example. So program counter indicates the address of the next instruction that is to be executed. So my example is that I am at second instruction. So now PC contains the address for the third instruction because I am at the second instruction and I have to execute next instruction, that is third instruction, that is available or that is made by the program counter. Next is the integer register file contains 8 named locations storing 32-bit values. These registers can hold addresses or integer data. So next one or next part is of IA32 is register that contains data that is used for location or for storage purpose. So first part is your program counter that stores the address for next instruction. Then is your register that stores the data with the help of 32-bit values. Then next is your condition code register that holds the status information about the most recently executed arithmetic or logical instruction. So PC contains address for next instruction, index address or index register file contains or store the whole assembly language program. Condition code registers holds only the ALU operations, that is arithmetic and logical operations. It stores intermediate results, basic results as well as the output results. So it holds status information about the most recently executed arithmetic or logical instruction. These are used to implement conditional changes in the control or data flow, such as is required to implement if and while statements. So condition code register contains all the registers that requires control or data flow like if and while statements. Next is your a set of floating point registers store floating point data. So these are the multiple parts which stored in IA32 assembly language programs. Now next part is your x82 that contains 64 bits. So first one is your IA32 and next one is your x86 64. So the first point is it mostly have two operand instructions. So it is of two operand instructions. It contains mostly two operands. Next, unfortunately, two prevalent syntaxes. One is Intel syntax, OP, DST, SRC, that is destination, this is source, AT&T, GCC, gas syntax, that is, this is Intel syntax, OP, DST source, this is AT&T syntax, that is OP, SRC, means first of all SRC, then destination. Next point says we will always use AT&T syntax, means we will always use first of all source and then destination. But a lot of documentation uses Intel syntax. So means this is a choice whether you use Intel syntax or use AT&T syntax. But this says we will mean assembler always use AT&T syntax for writing the codes of assembly language programs. These are the multiple examples. Move EAX to EDX means it will move the EAX value to EDX value. This is a pseudocode. EDX has a value EAX. This will move 0x123 to EDX. This is EDX equals to 0 into 1 to 3. In the same way, this will move this value to this one, this value to this one, this value to this one. This is the move that moves from one variable to another variable whenever we move in assembly language program. So this is how we can use x86-64 assembly. So these are the multiple histories which I told you in last class before the break. For the next part of presentation, we will focus only on IA32 instruction set. We will then look at the extension of 64 bits via x86-64 towards the end of the chapter. Means as although there are two types of assembly language instruction, that is IA32 and x86, but we will focus on IA32 instruction only. But we will see x84, 86, 64 towards the end of the chapter. Now, next topic is your machine code. But before this, let's take the book, what is available in book. First one is your machine level code, the same. This is machine code. Machine code is only language a microprocessor can process directly without a previous transformation. As I told you, machine level language is a program that uses 0 and 1 for writing the code. So this says machine level language is the only language that a microprocessor that a CPU can, microprocessor means CPU can execute directly or process directly without a previous transformation. As I told you, in high level languages we use compiler or interpreter. In assembly language program we use assembler. But if we are using machine level language or machine code, so there is no requirement or there is no provision for translating from one part to the another part. So it can work directly, means we can run directly the machine code, or the CPU can run directly machine code that is available in zeros and ones. Currently, programmer almost never write programs directly into machine code. Why? Because it requires attention to numerous details which a high-level language would handle automatically. So if I am using machine level language program, so it is more difficult for programmer to use those languages, because that looks like a tedious. There are so many syntax which I have to write with the help of C programming language. So it's better to use high-level language program that has some predefined syntax that is used for writing the programs, and also requires memorizing or looking up numerical codes for every instruction that is used. For this reason, second generation programming languages provide one instruction level on top of machine code. Means that's why we are not using machine level language, because this is very tedious and we have to write each and everything manually. Even in the earlier days of coding on computers like TH0 and PDP-1, the first thing that the MIT hacker did was write assembler. So this says as a machine level language individually does not solve the purpose of programmer, but we have to use either assembly language program or machine level language program or high level language program for writing the code, and then translate that code, means written in either high level language. So translate that code by using the compiler or interpreter, or if we are using assembly language program, then uses assembler for translating the assembly language program into the machine level language program. So this is the machine code that is written in zeros and ones. So this is also the same example. This says computer system employ several different forms of abstraction, hiding details of an implementation through the use of simpler abstract model. Two of these are used for machine level programming. First, the format. And then another one is set architecture, that is instruction set architecture or ISA. Most ISA includes IA32 and x86-64, which I told you earlier. So the full form is ISA is instruction set architecture and IA full form is instruction architecture. This is the compiler does most of the work in the overall compilation sequence. As I told you, it converts high level language into machine level language programs. These are the multiple procedures, or these are the multiple commands which is stored with the help of IA32, which I already told, PC, index register file, condition code registers, and set of floating point registers. So these are the same example. IA32 contains 4 GB or 4 gigabyte range. Now, next is your code examples. So now let's talk about these terms in C language. This is the C language code. that is code.c. There is a name of the file. First one is int a at a-c-u-m, that is accum equals to 02. Means first of all declaring the variable that is a-c-c-u-m accum that have a value only 0. Next uses the function. Function name is sum. It has a return type int, that is it returns the only integer values. Then there is a parenthesis, there is a bracket, and in bracket there is a term int x comma int y. Means there are only two arguments which sums the value, means it sums the value that is x and y. Then bracket close. Then curly braces start. In t is new variable that adds the both the value, that is x plus y. So takes next variable that is your t, it adds the value that is x and y and put the result into the t, that is of integer type. Now accum plus equals to t means t contains the accum plus values. Accum plus values means whenever we add 1 to the accum that is stored in t, that is a new variable, so t equals to accum plus 1. Now 1. Now t contains 1. Then return t. So this returns the value that is written in C language program. To see the assembly code generated by the C compiler. If I want to see how assembly code will be generated automatically by the C compiler, then we use the -s option on the command line. So go to the command line, that is go to the MS-DOS, use gcc -01-s code.c. This is the file name code.c. This is the options, s is used. So use gcc -01-s code.c. This says this will cause GCC to run to the compiler sorry, to run to the compiler, generating an assembly file source and go no further. Normally it would then invoke the assembler to generate an object code. So this is the object code. This is sum. First of all push, that is EBP. Now move ESP value to EBP. So first of all push means pushes the EBP variable into the memory, then move the ESP value to the EBP, then move 12% EBP value to the EAX, then move 8 EBP into AX, and so on. At last pop. Pop means inserting into the memory. Push means inserting into the memory, and pop means removing from the memory. This is how we can write or how we can convert the code in assembly language program. So this is the code in assembly language program. Push, move, add, pop, read. That is set. These are the multiple examples. This is another code, int main return sum 1,3. Notes on formatting. This is another example how we can format. This is int simple, int pointer xp, int y. Now add xp int plus y. Same example, pointer xp equals to t, return t. If I want to compile, this is a compilation. This is in assembly language program. Push, pop, move. Next topic is your data formats, but I think this is a new chapter, so that's all for today's session. From tomorrow, I will start with data format, that is topic number 3, that is data format. But before giving the doubts, let's take a quick review of the today's class, what we have covered in today's class, and then please text the doubts so that I will answer you all the doubts. So let's take a quick review what we have covered in the today's class. In the today's class, I started with chapter number 3, that is machine level representation of programs. This chapter contains 15 topics. This chapter contains 15 topics, that is historical perspective, program encoding, data format, accessing information, and so on. So I am starting with, or I have completed only 2 topics, that is historical perspective and program encoding. This is assembly language. What is assembly language? How we can use the assembly language? What are the tools available like assembler, compiler, interpreter? Then we have talked about mnemonics. What are the mnemonics available? What is mnemonics while writing the assembly language program? This is the diagram of different programming languages like machine language, assembly language, high-level language, that is C, Fortran, Pascal. Next, we also talked about some overview of assembly language, why we are using assembly language, how we can interpret the assembly language. Next is there are 2 types of modes available in assembly language. One is real mode, another one is protected mode. And we will focus more on 32-bit instructions, that is ALU, stack, other stack instructions. Now, next we also talked about key concepts like assembler, 2 number of passes like 1 pass assembler and 2 pass assembler. Next is your IA32. We have talked about 2 types of assembly language, that is IA32 and x86-64. So IA32 have a syntax, have a format. This is a format. This is a syntax for IA32 assembly language. Then next is your example, means what is the example that we can use in IA32. This is the example that is written. First one is your label, then mnemonics, comments, and mnemonics is always used whenever there are operands. These are the multiple storage devices. These are the multiple parts which IA32 assembly language uses, like program counter, index register file, code, condition code register file, and floating point register. Then we have also talked about some overview of x82-64 assembly. Then there are multiple histories of assembly language, multiple history of programming codes. First of all 8086, then 80286, i386, i486, Pentium, Pentium Pro, Pentium 2, Pentium 3, Pentium 4, Pentium 4e, Core 2, i7. These are the multiple extensions which is used while using the assembly language program. First one came in 1978, and then at last in 2008 there is a Core 7, as well as in 2010 there is a Core 7 also, i7. Next we have talked about machine code, that is used by not used by programmers because that is written in 0 and 1, and we have to see multiple options, multiple operations while using the machine level language programs. So that's all for today's session. Thank you. If you have any doubt, then please text the doubt. Let's see book. In book we have covered the same topics. These are the same topics. We have covered these topics: machine level code, then multiple processors, program counter, code example, C code examples. These are the multiple instructions that is stored by IA32. Then how we can notes on programming, or how we can perform the notes on programming. Then data formats. This I will cover in tomorrow's class. So that's all for today's session. Now, if you have any doubts, then please free to ask from me, text the doubt, and I will answer you. So that's all for today's session. Tomorrow we will cover topic number 3, that is data format of the same chapter. So thank you so much everyone.